is the first time since the pandemic that we have, an in-person colloquium, so we are trying to do then a hybrid one, from Zoom and in person. So we are taking advantage that Luis Garza from University of Colima is visiting us. So he's going to talk about the classical orthogonal polynomial and generalization of matrix case. Okay, thank you for coming, and the floor is yours.
Thank you. Well, first of all, I want to thank all of you for the opportunity to speak here, your colloquium. Especially thanks to Wilfredo for the invitation. Chicago is a very nice place. I'm very happy to be here. I will talk about classical orthogonal polynomials in several contexts. I want to mention that this is a joint work with Edinson Fuentes, which is a former student of mine, who works at Universidad in Colombia. And this talk will consist in 4 parts. The first one, which I think is the basic one, is related to orthogonal polynomials in the real line. Then in the unit circle, and then generalization of both cases to the matrix case. I will speak about that in a little bit. The question that I will be trying to address in all 4 sections is the same. The question is, what are the sequences of orthogonal polynomials that are classic, right? Classic. So there are some work done in all these areas. Actually, the last one, this one, is our contribution to the subject. But of course, I want to start from the beginning and try to show you what work has been done and what are the questions that we usually ask here. Okay, so we start. I'm pretty sure that probably the audience, unless probably only Wilfredo is the one that understands these things or has experience with these things. I'm not sure about the rest of you, so I will present a brief introduction to the subject. Yes. Okay, some background here. The first examples of orthogonal polynomials on the real line appeared in the 18th century, mostly related to some applications, for instance, the study of celestial mechanics. And then general theory started somewhere in the 19th century with the works of Chebyshev, Markov, Stiglitz, and many others. I think the most known cases are classical families. The classical families are Jacobi, Laguerre, and Hermite polynomials. I think they're very well known outside of the orthogonal polynomials community. It's very well known because of their applications. There are basically 2 theories. The first one, which is orthogonal polynomials on the real line, where the orthogonality is defined in terms of a measure which has support in the real line. The second one is the measure is supported on the unit circle. We will see that the theories are analog, so there are similarities, there are of course differences. And there are several generalizations. The one that I will be talking about here is matrix orthogonal polynomials. They happen when instead of having one measure, you have a matrix of measures. And the polynomials which are orthogonal with respect to those matrices are polynomials with matrix coefficients. So I will talk about that. But there are some other generalizations like orthogonality in several variables and multiple orthogonality when you have different measures. There are like the most famous generalizations of this topic. They have several connections with other subjects such as continuous fractions, moment problem, approximation theory, special functions, and they of course have many applications. I think the most famous one is quadratic formulas in numerical analysis, mathematical physics, where most of the motivation initially comes from mathematical physics. Also in probability theory and signal theory and digital image processing and many others. Okay. So start, this is the definition of orthogonality. We'll consider positive real functions, mu, which is supported some subset of the real line. Most of the time, this is an interval. We define linear product with respect to that function, and of course, we define orthogonality with respect to that linear product. Sometimes, or most of the time, this is actually a measure, but in most cases, the measure it has a weight, right? And sometimes this is called the orthogonality weight. There are some conditions. For instance, if the support is not bounded, then we require all the moments exist. This is normally achieved by imposing that the measure has some exponential decay, for instance. This is one of the ways that we can consider this. These are called the moments of the measure or the moments of the function. We can consider the ground matrix associated with those moments, which are Hahn matrices like this. And it's very easy to prove that when the measure is positive, then all of these matrices are positive definite. We can also ask a converse question that given any arbitrary sequence of moments, is there a measure such that those are the moments for that measure? And the answer is yes, if some positivity conditions in this matrix are satisfied. And this is known as the moment problem. Okay. There are several properties that these polynomials have. I think the most famous one is probably the three-term recurrence relation. We can construct the polynomial of degree n plus 1 if we know the polynomial of degree n and degree n minus 1. And there are some coefficients that appear here. These a's, they have to be positive, the b's have to be real, then you have some initial conditions, right? And there's also a converse result, which is called the Favar's theorem, saying that given arbitrary sequences of positive numbers and real numbers, if you start with initial conditions, then you can define a whole sequence, and that sequence is going to be orthogonal with respect to some positive measure, right? There are also properties of the zeros, which are very well known. The zeros of each one of the polynomials are simple, are real, and they are located actually in the complex hull in the interior of the complex hull of the support of the measure. And also they have this interlacing property between any two consecutive zeros of Pn, there's exactly one zero of Pn minus 1. These are very well known properties of these polynomials. Orthogonality can also be defined in a more general context with respect to linear functionals. So if we consider a linear functional u, which is defined in the space of polynomials, then we can also define orthogonality with respect to the functional in this way. Right? So we can also define moments associated with the functional. It's a very similar way. And we can guarantee that such orthogonal sequence is going to exist if and only if the determinant of the Hahn matrices of the moments are non-singular for every n. And we can also have a three-term recurrence relation in a Favar theorem, but in this case, there are some more, the conditions on the constants are not so restrictive. In this case, for instance, these, they have to be positive in the case of a measure. In this case, it's just enough to be different from 0. These b's, they have to be real. In this case, they can be just complex ones. But we still have a... The only condition in U is that it is linear and that the moments satisfy some conditions. Right? That's all. Not every linear functional has a sequence of orthogonal polynomials. You have to consider the moments, consider these matrices, and all the determinants of these matrices, they have to be different from 0. That's the condition. Right? Okay. So yes. One thing that you lose in this more general case is that the properties of the zeros are lost. Then you don't know much about the zeros in this situation. And you recover the case of the measure if the determinant if the sequence of moments of the functional is such that the determinants are positive. Right? So this is equivalent to the existence of the matrix. Right? So this basically, we say that this is a positive definite functional if the matrices have positive determinant, and in this case, this is equivalent. I mean, the functional has an integral representation in terms of a metric, which is positive, and that's it. But in the more general case, this is called regular or quasi-definite. In that case, you don't have positivity, but you can still have orthogonality, and some of the properties are still satisfied. Okay. So we're going to say that a family of the sequence of polynomials is classical if the sequences of the derivatives is also orthogonal. That's the definition that we're going to have here. It's not the only one. And if the sequence is orthogonal with respect to some positive measure or some linear functional u, we also say that the functional or the measure are classical. And the classical families, as I mentioned in the beginning, are the Jacobi polynomials, which are orthogonal with respect to this positive weight, the Laguerre polynomials, which are orthogonal with respect to this weight, and the Hahn polynomials, which are orthogonal with respect to the normal distribution. This is the bounded case, this is the semi-bounded case, and this is the unbounded case. Right? So there are, and this property of being classical is sometimes is also called the Hahn's property. It's the same. Okay. So there are several characterizations of the classical properties for orthogonal polynomials on the real line. The first one, this is actually sometimes people define the classical orthogonal polynomials are the polynomials that satisfy this second order differential equation. Right? So all of the definitions are equivalent. So these families also satisfy this differential equation, where these are polynomials with a fixed degree. This one has to be degree at most 2. This is degree exactly 1, and these are just constants. Okay. The other property is that they can be expressed in terms of a Rodriguez formula like this. In this Rodriguez formula, the weight appears, and also the polynomial that appears here in the differential equation. All the classical families satisfied, they can be expressed in terms of a Rodriguez formula. Another property is that they can be expressed in terms of hypergeometric series. This is also very well known. And the last one is that the orthogonality weight or the functional satisfies what is called a Pearson differential equation, which is this differential equation that involves the weight, orthogonality weights, and the polynomials that appear in the differential equation. Right? So all of these properties are equivalent, and they are also equivalent to the fact that you have a sequence such that the sequence of derivatives is also orthogonal. It's everything the same in this situation. Okay. So this is the classification in terms of the polynomial that appears as the coefficient of the second derivative in the second order differential equation. And this must be a polynomial of degree at most 2. And we have a different family depending on the degree and the nature of the zeros. For instance, if the degree is equal to 1, then you have the Hahn polynomials. If the degree, the degree is equal to 0, then you have the Hahn polynomials. If the degree is equal to 1, then you have Laguerre polynomials. If the degree is equal to 2 and you have different roots, then you get Jacobi polynomials. And if the degree is 2 but you have a real repeated root, then you have Bessel polynomials, which satisfy many of the properties that I mentioned before, but they are not considered classicals because they correspond to the case where the orthogonality measure is not positive. But they also satisfy some of the properties that I mentioned before. Okay, so these are, I think, probably the most known cases of orthogonal polynomials because they have many applications. Now we go to orthogonal polynomials on the unit circle. So just to summarize, for orthogonal polynomials on the real case, we only have 3 families of classical orthogonal polynomials, which are Jacobi, Laguerre, and Hahn. That's it. Now we can ask the same question for orthogonal polynomials on the unit circle, and the results are a bit different. Because now orthogonality is defined with respect to an inner product, which is defined in for complex polynomials in general. Then we have a measure or a function which is positive on the unit circle. And of course, orthogonality can also be defined in terms of a linear functional, as before. But now the linear functional has to be defined in the linear space of Laurent polynomials. You have to consider positive and negative powers of the variable. But other than that, this is pretty much the same as the real case. Of course, orthogonality can also be characterized in terms of the moments. Now you construct the sequence of moments, but now you have a Toeplitz matrix, but the conditions are pretty much the same. So everything is more or less the same. It also has some properties, also has a recurrence relation, but now it's called a pseudo relation, where you can still construct the polynomial of degree n plus 1 in terms of the polynomial of degree 1. The only difference here is that now in the pseudo relation appears this polynomial, which is called the reciprocal polynomial, which is a polynomial that you get from the original one by switching the coefficients and conjugate, right? Something like that. It's also called the reverse polynomial. These numbers that appear here are called Bernoulli coefficients, reflection parameters, Chu parameters. They have several names, and they play the same role that the A's and the B's play for orthogonal polynomials on the real one. And they satisfy that they are located on the unit disk, right? In the positive definite case. In the regular or quasi-definite case, they satisfy that the norm is different from 1. And in the definite in the positive case, we also have the property that the zeros of the polynomials, they are on the unit disk. Or if you have a regular case, not necessarily positive, the zeros satisfy that the norm is different from 1. Right? So,
remind me, what is quasi-definite case?
Quasi-definite is regular, is that in the matrix of moments, you just have that the determinants are different from 0.
Not positive.
Not necessarily positive. If everything is positive, then you have the positive definite case, you have a measure, which is positive, and everything is, you have a linear product, everything is the same. But if the moments are such that the determinants are only different from 0, then you can still define orthogonality, but with respect to the function. It doesn't necessarily have an integral representation with respect to a positive measure. But I mean, you lose some properties, but you still have orthogonality. Is that okay? Okay. So we have these properties, and now the question is: are there families of classical orthogonal polynomials on the unit circle? Right? Because we know that in the real case there are 3 families. Now we ask the same question here, and what happens here is this is something that was developed by Paco Marcellan and Pascal Maroni in more than 30 years ago. And they proved that the only sequence of polynomials orthogonal in the unit circle, such that the derivatives are also orthogonal, is the polynomials associated with the Lebesgue. This is the only one. And of course, you can see here that if you take the derivative, you have the same polynomials for a constant, which of course doesn't affect the orthogonality. So this is the only family with that property on the unit circle. And equivalent, this is the same as saying that a sequence of polynomials in the unit circle is classical if and only if all of the Bernoulli coefficients are 0, because if you remember, these are the Bernoulli coefficients, right? And of course, if this is 0, then the next polynomial is just times c, and then you have c to the n, right? So this is an equivalent condition for a sequence of orthogonal polynomials on the unit circle to be classical, that all of the Bernoulli coefficients are 0. So we have this difference between the two theories. In one, there are 3 families. In the other one, it's just 1 family. And now, we're going to extend now the question to what happens in the matrix case. Right? So we first consider classical matrix polynomials on the real line. Right? And now, just some definitions. So we consider now the space of matrix polynomials, which are polynomials, such that the coefficients are matrices. Of course, square matrices, complex in general. This space can be seen as a bimodal over the range of complex matrices. This is a basis of that bimodal, right? This is the identity matrix in that size. Of course, when I put this sub-index n, that means up to degree n, right? And we can consider the space of functionals. This is not really a functional, right? Because it takes a matrix polynomial and returns a matrix, right? This is the analog of the dual space, right? This space. And so this is just, this is linear. And if you give a polynomial, a matrix polynomial, it gives you a matrix. That's all. Okay. Now, given this functional, we can define another functional which is multiplication by a power. Right? Now, the definition is like this. This is something usual definition. You define this new functional, which is the original 1 times a power, just by applying the original functional to the polynomial times the power, right? Okay. So because this is linear, of course, you can extend the definition for a polynomial. So you can multiply a linear functional by a polynomial like this, and of course, it's just the linearity of the linear function. Right? Now, every linear functional defines a matrix's linear form, which is something like this. So now you have something. This is the analog of the inner product in the scalar case. Now you take two matrix polynomials, and the result of operating them under this linear form, it gives you some matrix. Okay. So this is U is like the linear functional, and this is the linear form is more or less like the inner product. And of course, once you have an inner product, then you can define orthogonal, right? Okay. So these are the properties. We have linearity, this is additivity, and this is more or less homogeneity, right? We can also define the adjoint of the linear functional by using this matrix multiplication, right? We will say that a functional is Hermitian if it's the same that the adjoint, which is more or less standard. We will say that U is positive definite if this matrix is positive definite for every matrix polynomial. And in that situation, it is possible to prove that this linear form has a matrix, an internal representation in terms of a matrix of matrices, right? So this is pretty much the extension of what we know in the scalar case. Okay, so everything is more or less the same. Of course, we have the problem here that multiplication of matrices is not commutative, so we need to make sure that we multiply on the right side, I mean, either the right or the left. But there's a difference because we don't have commutativity. So other than that, this is pretty much the same. Okay, so now that we have all of that, then we can define orthogonality. We will say that a sequence of matrix polynomials is orthogonal with respect to the functional. If it's orthogonal with respect to the associated linear form, so this is that when you consider this with smaller powers, then you get 0. And if k is equal to n, then you have some matrix which is invertible. So these matrices are more or less the equivalent of the norm. Is that okay? But this is not really a norm because these are matrices. Okay. Of course, we will say that they are orthonormal if these matrices are the identity, right? And we will say that these polynomials are monic if the leading coefficient is the identity matrix. So pretty much the same. Now, they share most of the properties that are satisfied by the scalar orthogonal polynomials. We can also have a characterization in terms of the moments, but now the moments are matrices, and now the Hankel matrices are Hankel by block, right? So they are block matrices that are Hankel, right? If all the determinants are different from 0, we say that the linear function is quasi-definite as before. Of course, matrix orthogonal polynomials are unique up to multiplication by invertible matrices, which is more or less what happens in the scalar case. You have uniqueness except for multiplication by a constant. In this You also have a recognized relation. The only difference is that now the coefficients are matrices, right? In this case, the scalar case, these are supposed to be different from zero. In this case, they have to be invertible. I think this is no. These are supposed to be different from zero. Now they have to be invertible, and these can be just any matrix. Okay. And I'm multiplying on the left in this situation, but we can define orthogonality also on the right. In this situation, I mentioned before that because of the non-commutativity, it's not the same to multiply on the left than multiply on the right. But in this particular situation, it doesn't really matter in the sense that if you multiply on one side or the other, the resulting orthogonal polynomials, one is the transpose of the other. So it doesn't really matter. So you have a family on the left, you have a family on the right, but one is the transpose of the other. So it doesn't really matter what side you choose when you're gonna multiply. At the end, it's the same. As long as you do everything like consistently. Okay. So now we will define classical matrix orthogonal polynomials on the real line, and we will use the definition given by Cantero, Morales, y Velázquez, which are they work in Universidad de Zaragoza in Spain. This is more recent. This is from 2007, and we will say that one way to characterize orthogonal polynomials in the matrix situation is this is similar to what happens in the scalar case. U is a matrix classical functional in the sense that the sequence of derivatives are also orthogonal if and only if the linear functional satisfies a Pearson differential equation. Right? This is the derivative operator. Of course, everything is matrix. Now, this is a matrix polynomial of degree 1. This is a matrix polynomial of degree at most 2. But everything is pretty much the same. Right? Now, they prove that this characterization is satisfied. And not only that, they also prove that if P is a classical family and the sequence of derivatives is also orthogonal, then this sequence of derivatives is orthogonal with respect to this functional that can be obtained from the original functional times the polynomial that appears here. Right? So it gives you the relation between the two functions. Okay. So, of course, when the matrix polynomials that appears in the Pearson equation is a diagonal matrix polynomial, which means that the matrix coefficients are diagonal matrices, then of course this is just a simple extension of the scalar case, because now you work individually in each component, right? And then in this case, you get exactly the same families that you have in the scalar case. So you have Hermite polynomials in the case where the degree of this polynomial is 1, Laguerre polynomial when the degree of this polynomial is, this is 0 again, this is degree 1. Jacobi type polynomials when you get a polynomial of degree 2, and you also have the Bessel polynomial.
But they are matrix.
Now they are matrix polynomials. Now these are matrix polynomial with diagonal.
And when you see the diagonal, is just a classical polynomial?
Yeah. So it basically it's like having a classical scalar polynomial in each location of the diagonal. So it's pretty much the same. Of course, the most interesting case is when you have matrix weights or matrix polynomials that are not diagonal. For instance, in this case, having a diagonal polynomial here is pretty much the same. You get the same results when the matrix weight is diagonal. I can never pronounce that correctly, but you know what I mean. Okay. So yes, when this happens, then of course you can take one matrix at each side. In the center you have diagonal things, and everything gets multiplied. But at the end you still have a diagonal case. So these cases are not really interesting in the sense that you get the same thing that you had in the scalar case. So the interesting case is when you don't have this. When you have a non-diagonal case that you cannot diagonalize. I said that correctly, right? So yes, so this is an example. This is an example to a matrix of size 2. This is, of course, polynomials that are related to the Hermite polynomials, right? But now the matrix weights multiplied by this matrix, right? And this is not something that you can diagonalize. In this case, if you have this matrix weight, and this is the polynomial that appears in the Pearson equation, right? This has degree 1, right? And you have, this is the other polynomial, also has degree 1, right? Now, in this situation, you can show that the orthogonal polynomials with respect to this weight are not diagonal. And they don't fit in any of the previously known categories. They are not Jacobi, they are not Hermite, they are not Bessel, they are not Laguerre. This is something else. This is something else. So that means that unlike the scalar case, when we only have 3 or 4 families, depending on if you count Bessel or not, there are actually many families satisfying this Hahn property. Many classical families, they are not the original ones, the scalar ones, right? So a complete characterization is actually an open problem. There's this recent contribution by Garza, I think he's close to Los Angeles, and they attempted a characterization of matrices of orthogonal polynomials, which is similar to what Lochner did in I don't know several decades ago. Right? These guys they consider not the Pearson equation, but the second order differential equation, but now with matrix coefficients similar to what Durand did. Okay, so there's some work done. I mean, there are some known families, but there's not a complete characterization so far. Okay, so this is what happens, and now we go to classical matrix orthogonal polynomials now on the unit sequence. This is actually our contribution to the subject because everything that I mentioned before is somebody else's work. But now we had a hope here that since in the real case, when you consider the matrix extension, you have more families. So we're thinking maybe if you consider the matrix case, but for orthogonal polynomials on the unit sequence, you will have more classical families, not only the one that I showed before, which are the Lebesgue case, the powers of C, right? But it turns out that the only family is exactly that one. I mean, there are no more families here. It's the only one, which is kind of strange, because we were hoping that something similar to what happened in the real life will happen here. But it doesn't happen that way for some reason.
Is it because like you can diagonalize in the complex numbers?
Maybe.
Right, because with real, the thing that breaks it is the
Yeah,
complex
but in
rates.
the complex case, I mean, you have more matrices, but not every complex matrix can be diagonalized in the complex matrix.
Okay.
Only matrices that are normal, right?
Okay.
So that's probably not. I don't know. I don't know.
So you get the same result as Mastrigliano.
Exactly the same result. Exactly the same result. And we were hoping to find like more families, right? So we can work more.
Yeah.
But no, it's the same family. So let me just show you what we did. It is surprising. I will tell you this at the end. Okay, so in this case, of course, the same way that you extend standard real orthogonal polynomials to the matrix case, it happens here. You also have a matrix functional, but now defined in the space of Lorentz matrix polynomials. You have positive and negative powers, right? Of course, they take you to matrices that are complex. You ask for this guy to be Hermitian because you need that in order to have a cislinear form, everything to be regular. Of course, you have a basis here. In this case, we still have that matrix multiplication does not commute. But in this situation, then you need to be very careful because multiplying on the left is not the same as multiplying on the right. And it doesn't happen what happens in the real case. When it doesn't matter how you multiply. At the end, you have exactly the same polynomials, and you get the output. For instance, you have the left polynomials, you take the transpose, you have right polynomials. That doesn't happen here. Then the families could be different. The left polynomials and the right polynomials, they can be different. So there's no relation between them. Okay, so which is also strange. Yeah. Okay. So we have the same definitions. The matrix function is linear if you have this homogeneity and additivity. Of course, I'm putting here on the left, on the right, right? So this is not the same, right? One is on the left, the other one is on the right, but it's the same problem, right? Now, you can define, of course, matrix multiplication in the same way as before. You multiply first the power, and then you use linearity and extend it to a whole polynomial. This is pretty much the same. Of course, now I'm running the two expressions because one thing is on the left, and one thing is on the right, but it's the same definition, but you work in a different side of the form. Now, every linear functional induces matrices linear forms, one for the right, one for the left, and you have exactly the same situation as before, exactly the same. Now with these forms, you can get two matrix polynomial. It gives you a matrix, okay, complex matrix. Okay, we can define orthogonality, but now we have two sequences on the left, on the right, and of course the ones on the left are orthogonal with respect to the left linear form. The one on the right orthogonal with respect to the right linear form. These matrices are the equivalent or the analog of the norms. Okay, these are matrices, and we have exactly the same definition. These are not singular. If these are equal to the identity, then you say that the family is orthonormal. If the leading coefficient of each polynomial is the identity, you say that the family is monic, so everything is the same. And of course, we want to say that they are classical, the same, if the sequence of derivatives is also orthogonal. So it's the same definition. Now, it happens, same thing. The existence can be characterized in terms of the moments, which are now our matrices. So now you have block depth matrices, and of course the existence can be characterized in terms of the determinants. Same as before. In the positive definite situation, then you have a matrix, an internal representation in terms of a matrix, which are now matrices on the unit circle. Everything is the same. You have stable relations, but here's the difference, and this is one of the complicated things. Now you have two different Segor relations, one for the right and one for the left, but they are mixed in the sense that when you consider the Segor recursion for the right polynomials, you need to include this term, which is from the left polynomials, and the same happens here. If you want to construct the left polynomials, you need information on the right polynomials. So basically, they are like mixed, and you need both of them to complete it. Okay, so they have this relation. You cannot work separately. You always need to consider both families at the same time if you want to use this relation. Okay, so these are the stable relations, and the question is the same. The question is, I already told you the answer to this. The question is, are there families that are classical and they are not the Lebesgue case? The answer is no. And I'll just give you some idea of the proof. The main idea is that these matrices, these are the matrices Verbulski coefficients, they appear mixed again. These matrices play a key role in the analysis because everything depends on these matrices. The techniques that we use are similar to the ones that Paco and Pascal Maroni did. Basically, what we did is the following: they used the Segor relation to show that if the family of derivatives is orthogonal, then that implies that the Verbulski coefficients must be zero. That is what they did, right? Now we did the same, but the difference here is that the procedure is very similar, but some of the statements that some of the auxiliary results that they need, in order to extend them to the matrix case, you need to be very careful because now the matrices do not commute, and that makes some of the proofs more difficult. And the other thing is that in the scalar case, you only have one Segor relation, and now we have two. And that's the difference. And this issue about the commutativity plays a big role because there are some of the proofs that you cannot just extend. You have to make additional proofs. But other than that, the procedure that we use is exactly this one, exactly the same. Okay. So some auxiliary results. The first thing that we prove, of course, this is the original family. This is the sequence of derivatives, one on the right, one on the left. And the first thing that we were able to prove is that if we impose that the sequence of the derivatives is orthogonal, then we must have that the Bernoulli coefficients for the new family, they have to be the zero matrix from 3 and on, right? So they have to be. The converse is not true. You can find a family of polynomials such that the Bernoulli coefficients are 0, except for the first one, and they are not orthogonal. So you need all of them to be 0, right? And this is an example that we were able to construct. This is a matrix measure, very nice. 2 times 2. We consider the orthogonal polynomials with respect to this matrix weight, and we were able to compute actually the polynomials by using Hahn's formula. And the polynomials, both the right and the left polynomials in this situation is the same because the measure has this symmetry, right? So they are the same. And in this situation, you can see that for n greater or equal than 2, when you evaluate at 0, you get the 0 matrix, right? So the Bernoulli coefficients from 2 and above, they are 0. But when n is equal to 1, then you get 0 here, you get 0 here, and you get 1 half, minus 1 half here. So that means that the first Bernoulli matrix coefficient is not 0, right? And the rest is. But that non-zero coefficient is enough to prove that the sequence of derivatives is not orthogonal anymore, right? And we were able to compute everything. We compute the sequence of the derivative, which is very easy. The reciprocal polynomials as well. This is the first Bernoulli coefficient, which is this one. All of them are 0, the other ones. And then we prove that these new sequences does not satisfy the second relation because this term is not the same. And since it doesn't satisfy the second recursion, that means that it's not orthogonal. So then we have a sequence that not all the Bernoulli coefficients are 0, and you don't have orthogonality of the derivative. Right? So this is just an example. And now we were also able to prove that if we impose the condition that the sequence of derivatives is also orthogonal, then not only the Bernoulli coefficients of the new polynomial has to be 0, but also the Bernoulli coefficients of the original polynomials. They have to be 0 for n greater or equal to 3, right? So this is actually easy to do, but more or less, the actual problem is to prove that the other two are also 0. That is, we try like 2 years to prove that. So, yes. So we were able to prove that this is true if this matrix is different from 0. If you consider the case when the matrix is 0, then you need to go to do something different, something that didn't happen in this scalar case. So this was actually the difficult part. And this is the theorem. The theorem says once that you prove that from 3 and on everything is 0, then you have to work a little bit to prove that the first two are also 0, and then you have the result, and the result is this one. That if you have a matrix function which is regular, then it is classical if and only if it is the Lebesgue matrix function. And of course, that means that the only sequence of orthogonal polynomials in the matrix case that is that such that the sequence of derivatives is orthogonal is the same one. So it's just that case. This is the only case, which was a bit surprising, yeah, but this is what happens. Now, this is everything that I have. And now the only thing that I want to mention now is that I was recently presenting this in some conference in Valencia. And one of the people that was there, which is Luis Bergestar, which is a Mexican mathematician, which is recently working with orthogonal polynomials, he told me that maybe the issue here is that we are trying to force the derivative operator that the standard derivative operator, that it works well in the real line, but probably in this situation it doesn't work well because this is like the supported dimension is different, and this is like a complex derivative, and so we are probably trying to use the wrong tool. So he told me maybe you need to consider another operator that works in this case, which is like an analog of the derivative. Right? So that is probably why, like this is too restrictive. It's too restrictive in the sense that the only thing that satisfies this is just the standard the eigenfunction. So maybe we need to consider another operator, which is some kind of generalization of the derivative in this situation. So I'm asking you, if you know some operator which is similar to the derivative that works well in the unit circle with that symmetry, you can let me know, and we can work.
Yeah, because what you mentioned, it looks that the derivative, the complex derivative is similar to the real derivative, but it's not.
It's not.
It's much more. Right?
Exactly.
Right?
Exactly.
Because in the complex case, you have this marvelous thing that if you have the function is differentiable once,
It's
infinite.
differentiable. And that is being very restrictive.
Which is pretty exciting.
Exactly,
It's
exactly.
like,
Yeah, because analytic functions are like very restrictive in
Yeah.
that sense.
Yeah.
And I think that's the issue. No, I'm pretty sure that's the issue. So,
Yeah.
so what I need to do now is I need to find the correct operator.
Yeah.
That is, so if you have any idea, let me know, because I'm not really an expert in that in those things, so I don't really know. But now I know what to look for. So, yeah. So that is all. Thank you for the invitation. If you have any questions, you can ask.
Questions? Questions from afar?
you can check the chat. I don't know if the chat has anything or if it's just in case I can see.
Chat.
Yeah,
One question or comment.
My question. There was a question, but the question was answered. It is correct to conclude that the normal can be diagonalized. Yeah. This is what you
that was
asked about.
it. Okay.
Yeah. So yes, the question was answered. No, I think that was the.
The Duran definition, he started from the recurrent relation, or
Definition
it's
of-
equivalent to
Definition of classical or of
no, the matrix polynomial. Duran had
Thank you for coming. No, I think he. He starts by establishing an analog of the Favar's theorem.
the Favart.
So using the recurrent relation, but now with matrix coefficients instead of scalar coefficients, and then he goes from there. And these things, he studies these things, but based on the second order differential equation. So he starts asking, okay, does this polynomial satisfy a second order differential equation? And he goes from there. He actually has a lot of results.
Yeah.
But yeah.
Okay.
Okay. So no more questions.